All right, I've got the green light. I guess it's time to start. Oh, before I move on, thanks everyone for coming, making it all the way out here to the, almost into the lake, but we're let's, real quick, CPS team, we'd like to get your feedback on CPS, the product, features, things about it, not on this session in particular. You'll get your chance for that later too. But please take the survey if you find yourself dozing off in your after lunch nap. You can wake yourself up with a survey. I'll have this up again at the end if you don't remember what the URL is now. All right, I'm Greg Kazanza. I'm a program manager on the data center networking and platform team. I'm in the operating system group at Microsoft, and we're the team that actually builds Hyper-V network virtualization, the vSwitch, teaming, all the underlying infrastructure that runs for virtualization and the Microsoft Cloud platform. I've been deeply involved in CPS from the beginning, working on implementing the network architecture and making changes and adjusting along the way. And so I'm here to talk about what went into CPS and the cloud platform system. It's really been one of the, from my perspective, one of the first new products from Microsoft that really brought a lot of different teams together across Windows Server, operating systems, Azure, the Azure UI team, and across the board to really build an entire solution that really takes advantage of all these different technologies we have to offer. So with that, let's get in. I'd like to introduce you to CPS Guy. He's the happy new owner of a 4-rack CPS stamp. He's smiling and waving. I'll also introduce you to Do-It-Yourself Guy, who is buying his own hardware components, buying his own software components, putting them all together himself. And along the way, he'll go through several iterations trying to get it right. Some will look better than others. We actually felt this way many times during the CPS development cycle. He'll eventually have to call for support to get help from the different vendors that he's purchased from, and they'll point fingers at each other, figure out whose problem it is. But in the end, he'll build something that works, like all of you are doing today and all of you can do. It just takes it's a long road to get there. So whether you're a CPS guy who buys the complete solution that we have, we're showing on the show floor today, how many of you gone and seen the CPS rack that's there? Okay, those of you that haven't, I encourage you to go there and look at it in the booth and talk to the people that are there, and they'll tell you all about it. But regardless if you're a CPS guy or do-it-yourself guy, I want all of you to get something out of this session, to learn what we did in CPS, the advantages of CPS, so that even if you don't buy CPS yourselves, you'll be able to use the things we learned from it and the technologies in it for your own, your own builds. So what are the things we're going to cover? Of course, I'll talk about what influenced the network architecture of CPS, why we did things the way we did. Then I'll kind of work my way, kind of getting deeper and deeper into the system. First, with the out-of-box experience. These are the things that, if you buy CPS, these are the things that you would need to know to be able to use it, integrate into your environment from the networking perspective, get it up and running. Then I'll go deeper into the insides of CPS. These are the things that you don't necessarily need to know as somebody that buys or uses CPS, but you probably want to, and you're probably curious about, how do things work inside? Where do all those cables go if you look at the rack? What are they there for, and why do they do it? Why do we do things the way we did? So we'll talk about that. And then I'll talk about some of the performance tuning we did to get to the performance levels that we have in CPS. They really show what you can do with network virtualization really on any platform. So it's a really good example of what we can do. And I'll talk about the settings so that if you have your own environments, your own systems, you can apply those yourself. And also I'll talk about the reliability testing, really what do we put into it to make sure that CPS is reliable. If things fail, you'll continue to run without even noticing that anything went wrong. It'll give you time to fix it and work with our support team on getting it right. All right, so let's talk about the design principles. What went into it? You see 3 blocks here: System Center, Azure, and SDN, software-defined networking. These are really our building blocks. Because up front, we were kind of given this task of building an Azure consistent cloud in a box. And what does that mean? Well, it means that we have a lot of the same services that run in Azure, a lot of the same technologies running behind the scenes, and you get a lot of the same properties, but things that you can do and take into your own data centers, use along the way. if you look at what we have as a foundation for building a CPS, of course underneath you have physical infrastructure. This is provided by the Dell racks as our launch partner. Of course, there are 64 nodes here, so I think that's 16 CPS stamps. So if you want to buy this many, we'll be happy to swipe your credit card. But we layer on top of that hardware a set of core services and edge services that are part of the Windows Server platform and Hyper-V as a platform. We have network virtualization built in. We have DNS, DHCP, all the services that are available. There's the virtual switch, kind of got covered in the background, teaming, and then we have another layer of what we call edge services that are kind of used as a foundation to give the multi-tenancy, to really give you multi-tenancy in much the same way that Azure does. So we have a lot of the foundations in Windows Server already that we could use as the starting point. At the same time, we had built the Azure Pack as a way to expose the Azure services. So when we started CPS, we already had a lot of these tools available. And of course, we have VMM and the rest of System Center to be able to use for management. So we put all these together kind of as the building blocks from the Windows Server side of things. And so we use Cloud OS, now we call it Cloud Platform, as the platform for software-defined networking in CPS. So we didn't want to base it on just VLANs because there are a lot of reasons for that, and spanning L2 and creating per-tenant VLANs, and I'll talk about that going forward. The other thing that we took from Azure, and this is a slide from actually one of Azure's decks, is their embracement of technologies that let them get to hyperscale networks. So Azure is based on having layer 3 at all levels. So if you look at the right side, that represents Azure. The left side represents what a lot of typical data center network might look like that spans layer 2 across racks in different places in the data center. Azure uses layer 3 at all layers. They do everything through software. They build their fabric once. They set up their routing infrastructure once at the physical layer, and then they don't touch it. And at the same time, because they have L3 at every layer, they can scale really efficiently. They use what's called a CLOS-based design. It's a very specific type of architecture that gives you connections to every point from your switches. We'll look at that in a little more detail. So we took that from Azure as one of the influences, and we built that into CPS. So whether you're starting with 2 racks, you get an equal set of connectivity from the top of rack switch up to the layer that we then call the aggregate switch. So the top of rack switch layer, there are many switches there, but each one of those switches has a link to every layer above. And each one of those switches is a router. So your top of rack switch, that's a router. Your aggregate switch, that's a router. Everything going all the way up as far as you want to go is a router. And so as you add more racks with this CLOS topology, you get a linear increase in bandwidth so that your new rack 3 doesn't impact the workloads that are running on racks 1 and 2. They're not taking bandwidth and sending broadcasts over there into your other racks. And you get an equal number of connections now from your existing TORs into your new TORs or into your aggregate layer to increase the bandwidth linearly. So as you get more switches, you get more links. And so it really lets us scale, from 1 up to 4, and in the future we'll be able to go to much larger architectures as well. The other thing is these layer 3 technologies allow for switches that don't really need to do much. They're basically just doing routing decisions. They don't have to have any advanced protocols enabled like spanning tree or anything like that. So we can keep the cost of the switches down as well. And we rely on ECMP and BGP to handle if one switch goes down along the way, you have many other paths to get into your Hyper-V hosts and out to your border. So you always have more than one path. In many cases, you have multiple paths out. So now, though, one of the characteristics of this CLOS, this flat layer 3 network, is that every one of your racks now is in a different subnet. Now, if many of you have built environments like this, then that means that certain things traditionally would get anchored to those racks, and you can get asymmetric use of these racks. So that's where virtual networking comes in. Virtual networking is basically the technology that virtualizes your application and tenant address spaces. So basically, it lets you span the address space of the VMCs across all these different racks. And underneath the covers, Hyper-V and network virtualization is handling the translation between the virtual address space and the physical address space that your Hyper-V hosts and that's assigned to the racks. It's doing that behind the scenes in much the same way as it's translating the VM's execution into, from virtual CPUs into physical CPUs. Network virtualization is doing the same thing behind the scenes. So that also lets your virtual network start off on 2 racks. You add more racks, that same virtual network can span all those racks along the way. And then VM can move between the racks. You can get very efficient packing of your VMs within the environment. Of course, it also gives you very dynamic ability to create and delete networks as needed. As tenants come and go in these environments, as applications need new networks, you can create them. You can clone them, essentially, and make copies of them. So you can clone the VMs, and now you have a new copy of these VMs. You can test a new version. And so there's a lot of advantages. This is all managed through SCVMM. The logical switch kind of manages the infrastructure. And then as you work your way up through the Azure pack is how the tenants basically get their own self-service of being able to create these virtual networks along the way. So the other thing that was key that we built in, and we learned this from Azure as well, is load balancing. So as you get to cloud applications, you're going to be able to expose a single virtual IP that the client applications of your service will connect to, and then you have a number of services that can take advantage of the elastic nature of the cloud behind it. And then you can scale out those services. So we knew early on we would need to have a load balancing solution in there, and I'll talk more about that later on, about the load balancer that we include in with CPS. And then, of course, the user experience. In order to be Azure consistent, you, of course, have to have a UI that's consistent. Those of you in the back might not be able to tell as easily as those in the front which one of these is Azure and which one is the Azure Pack. I'm sure you've seen the Azure Pack by now and know it's a very good representation of the Azure UI. It gives you a very similar user experience as well. And it's fully integrated with network virtualization, so tenants can go and create their own virtual networks, add NAT. They can create their own site-to-site tunnels all through, and connect the VMs to these networks as well, all through the Azure Pack experience. So there are some things in CPS, though, that we didn't take from Azure. Not everything translates. We couldn't just take Azure exactly as it is and ship it in a box. This is a system that's been designed from the ground up to use Azure principles, but do it in a way that it would be valuable to all of you. One of the things that's different is how we handle resiliency, failure of different equipment, in particular network equipment. Azure Scale allows them to absorb much larger failures than I think many of you can absorb. If Azure loses a top-of-rack switch, and as a result they have no connectivity to the hosts below it, they lose 30 Hyper-V hosts at a time, to them that's a drop in the bucket. They'll just spin up the workload somewhere else. But if you're buying 1, 2, or even 4 racks and you lose an entire rack, well, that's not acceptable because you might not have the capacity to spin up those VMs elsewhere. So we built in a lot of redundancy into CPS. That's one of the key differences between us and Azure, is that in a CPS rack, you can always absorb at least one failure of the network hardware, and in some cases, with a lot of the software components, it's N+2 failure as well. The other area that's different is in the area of how the whole environment is managed. Because Azure has a whole team of developers. They've really embraced the DevOps culture. And their developers push out updates and manage directly through code. For a lot of you, you don't want to do that. What you do want to do is you want to have a UI where appropriate. You want to have consoles. You want to have PowerShell to administer it through scripting and automation. And so we built in System Center as the management infrastructure for that. Now, there are a lot of things that you get in CPS that aren't actually available to everyone else. These are things you could build yourself, but for CPS customers, we ship these along with it. These are the SMA runbooks that are included with CPS, so there's a lot of automation, especially around replacement of hardware. If something fails and you need to replace that hardware, we have runbooks to do a lot of the rebuilding, patching, things like that. There are a lot of runbooks in place, specifically and only available in CPS that are available for you. And then also some of the OM operations manager views and UIs tailored to CPS because it's very specific to the CPS architecture, and it gives you views directly into CPS for monitoring. All right, so let's see. When you open CPS, the racks just pop out of the box, and let's talk about what you can do with it. Basically on day one when we hand over the key, so to speak. Well, there are a few things before actually we do that you have to be prepared for, because obviously you have to hook CPS into your environment. Now, this first section kind of treats CPS as an appliance, because it really is, from your network perspective, like an appliance. There are very few things that your board or that you provide in your data center need to do in order to connect into CPS. And CPS itself is a very static configuration, because all the dynamic nature comes from network virtualization. We never touch the physical network once we've deployed it. We deploy that for you, configure it once up front, and then basically you never need to touch the physical part of it. But there are some things you have to do to connect it to the rest of your network. Now, we have a number of physical connections, up to 4 SFP plus connections, give you 10 gigabit from each aggregate switch. So again, as you increase the number of racks you get more aggregate switches, which increase your bandwidth linearly all the way up even to your border of your core network. So if you even have 4 border devices in your core network that you want to connect your CPS racks to, you can connect 1 from each aggregate switch up to that border. If you only have 2, you can actually connect 2 to each border. And that gives you a huge amount of bandwidth going up north-south. We also require 1 gigabit Ethernet. This gives connectivity into the serial port concentrator that we include in the environment. The serial port concentrator basically gives us direct control of the switches. Well, it gives you direct control of the switches, so that if something catastrophic happened, there's still a way in that's separate from the main routing infrastructure. So sometimes you have to plan ahead for having that 1 gigabit connection there. And then the load balancers. We actually include 2 hardware load balancers in CPS as well. The hardware load balancers sit outside of the CPS racks, but logically they're connected directly into the CPS racks. They don't connect directly into your core network anywhere. They go directly into CPS. They just sit outside of the racks themselves. And there's a huge amount of bandwidth available to those load balancers as well. As far as the border, well, it's basically layer 3 from aggregate switches up to the border as well. So we expect ECMP to be configured so that any path can be taken from your border down. You can use static routes, but we strongly recommend that BGP makes it at least up to the border. From there, you can transition to OSPF if that's what you use in your data center. But we need BGP up to the border at least. Well, we don't have to, but we recommend it. That also handles if you do have a failure of a switch, then BGP will automatically reroute the traffic as well. And then we have to have point-to-point routing between the aggregate layer and the border layer as well. So that gives you the point-to-point link between the routed link between the border and the aggregate. Now, when we start to talk about IP addressing, there are a number of subnets that we ask for up front. We call these supernets that we request that you need to give us so that we can allocate addresses and actually do all the configuration of the CPS network up front. So we actually will go into the switches before we deliver the CPS racks, and we fully configure it. But in order to do that, we have to know what your address space is. So this is part of the pre-survey that we ask for as we build out your racks before we ship them. So we ask for what we call a corp private. These are subnets that we'll route that we expect to route on and off of the racks. We ask for a /21 or /22 of address space. Now, because it's called corp private, it doesn't necessarily mean it has to go everywhere in your corp network. It could stop right at your border if you want to stop there. That's up to you to decide how far it goes. But basically, this is for traffic on off the stamp. It's how you'll connect into your management portals, for example, from the outside world. It's for any traffic that needs to go on and off the stamp for management purposes. So we'll allocate all the management VMs, the Hyper-V host management addresses come from these networks. The point-to-point links between the switches, because every link between a physical switch has to have a very small /31 subnet available. So we'll allocate that from the port private. We then have what we call stamp private that we ask for as well. This is a subnet. These are subnets that we never actually route off the stamp or don't have to. Now, you could give us address space from your corporate range if you want to for that. And we can use that as well. It's up to you, and then you can reach in directly. But you don't need to. You can give us the same subnet for each stamp. So if you do have multiple stamps, you can actually use the same stamp private subnet for every single one of them. Then we ask for a subnet we call external. This is one of the first, essentially, application or tenant address spaces that's available. External basically is used for all of these customer or outside world-facing addressing that's needed for the infrastructure. So it's used for site-to-site tunneling endpoints. It's used for NAT addresses on the virtual network. So the front end of the virtual network, if you say you want to use NAT, that network is going to get an address assigned. It will come from this external range. And then we have a number of what we call forwarding customer address spaces. These are address spaces that you define that just get routed in and out of the rack. You can do whatever you want with these address spaces. Each one will go into a virtual network, and you can make it as big as you want. And then you can have it as a shared network for all of your tenants. You can carve out subnets per tenant and put ACLs on them so that they're restricted, so they can't talk to each other. Or you can just make it so that you can use it for other specific purposes. Oftentimes, customers will carve out the first one of these forwarding CA to extend some of the management address space in the stamp so that you can add in extra third-party services as well. So these are address spaces. Now, you give us these 4 address spaces, and then it's our job then to take these behind the scenes before we give this to you. Internally, we run this tool that we call the IP address calculator. This is an internal tool, and actually, sorry, even though the screen's very large, the font is really tiny. You don't need to see the details of this. Basically, what we do is we feed in this tool. This is a tool that's internal to Microsoft. We take these subnets, and we then break it up into all the different places where they're going to be needed along the way. So this is going to actually output the results. You don't need to see the details, but you can see every single subnet we carve out. And that's one of the challenges of a layer 3 network, where every point-to-point link needs a subnet, is that you have to allocate a /31 for each one of those. So right where the cursor is now is all of those point-to-point links. Those are /31s. We allocate the subnets between the border and the point-to-point, transit networks between the forwarding gateways and the network, and then your management subnets as well. We then carve out a few larger subnets for network virtualization, load balancing, and other private networks. And then we actually go and allocate static addresses from here as well. This tool generates the static addresses that we pre-assign to the different components that are pre-installed as part of the CPS delivery. So here are all the compute node addresses for the BMCs, load balancer addresses, and different pools for VMs. These are all things that, when you do it yourself, you have to do this yourself. This is a tool that we built that we use for CPS for deploying it. You can see we also do IPv6 in here as well. Every CPS stamp is pre-configured with IPv6. You don't have to use IPv6 in it. If your core network doesn't use IPv6, then it'll never get used. But it's there if you do need it, so we're ready for IPv6 deployments as well. All right, a few other miscellaneous things. DNS. So we built all the services in CPS so that CPS itself can be an island. It has everything it needs to get up and running. It doesn't depend on an external DNS. Well, at some point it has to get addresses, but to do resolution outside of the stamp. But there's DNS in the stamp that's highly available. There's AD in the stamp that you can connect to your external AD if you want to, but you don't have to. And then one other thing that we need to connect to is NTP. The switches themselves, when we set them up, we have to give them an accurate clock. So we have to specify an NTP server in there as well. So we ask for that in our pre-survey as well. So the end result, and this video here basically shows you, the day we hand over CPS to you, these are the things that you can do with it. So you can open up Bing. You can go to the service management portal now. So this is going to log into the service management portal and log in as what you would do as basically as a tenant in the environment. So I'm logging in here. I'm going into the tenant portal. And here you see you can immediately start giving tenants access to your environment. Now, this environment has already been populated with networks and VMs, but you can immediately start creating virtual networks. These virtual networks can have multiple subnets. They can have many VMs connected to them. You don't have to set up all the infrastructure that was created behind the scenes. I'll go through it in the next part of this session. But when you first get CPS, you can go right in and start doing all these things that you can do today in Azure for the most part. Here we have a site-to-site gateway enabled. We have NAT access, so your virtual network has access to the internet. This site-to-site tunnel is connecting to, this is Northwest Trading headquarters. So we're going to show you, how that site-to-site tunnel works. And you can deploy VMs. These VMs can connect to those virtual networks that you created. So here this VM is already up and running. It's connected to that Northwind virtual network that we created. We're going to connect directly to the VM. And then we're going to show you that that virtual network is live, and it's actually going across the site-to-site tunnel that was established. So here comes the command prompt. We'll do a simple ping to a 192.168.0 address. So this 192.168.0 is actually the Northwind Trading headquarters corporate subnet. You can see the virtual network has the .1 address in the .1 subnet. And we'll do a trace route just to show you that it's going through the network virtualization gateway to get to the Northwind Trading headquarters. The trace route thinks a little while. So the 192.168.1.1 is the Hyper-V network virtualization distributed router, always the .1 of your subnet in a virtual network. The 10.254.254.2 subnet is always the network virtualization gateway. So this is as it transits to the edge of the virtual network. Now it's going across the site-to-site tunnel. That's where it's hitting now the other side. And the last response is from the router or actually the destination on the on-premises end of the network. So now we'll bring up a browser just to show you that it actually works. And going across the network. Yay, it works. The suspense was killing me. All right. So this is what you can do out of the box. I jump right into the tenant operations to show you that you don't have to set up all the infrastructure that goes on behind the scenes. But now, if you want to know what goes on, let's find out what's actually set up inside as we look inside the configuration. All right, so what's a Stamp made up of? Well, it's made up of one or more racks. It's broken down into network, compute, and storage, what we call scale units. Within the compute scale unit in particular, on the first rack, we have the management cluster. That only exists on the first rack. In every rack after that, we have what we call the edge cluster. This is where all of your network virtualization gateways run. These are 2-node clusters in an active-passive configuration so that you can lose a node of either node, and your networks will continue to operate. And of course, we have the compute clusters that run in there as well. Now, on your racks 2 through 4 in each Stamp, we just have the edge compute. We don't replicate the management cluster across those. We include an edge cluster in every rack so that, again, we can follow the linear increase in bandwidth going. As you increase your rack, your bandwidth increases, and you don't take away from the bandwidth that's already available to your first rack. So if we dive into that network scale unit, let's take a look at what's inside there. What are all the switches? If you go to the booth and you actually look at the rack, you'll see all these switches up top. This is essentially an expansion. I actually might not have them in exactly the right order. I think the BMC might be at the bottom, but for this purpose, it doesn't matter. At the top of every rack is an aggregate switch. This is basically your highest layer that connects out to your border. It connects down into a set of actually 5 different switches per rack. One of them is the BMC. The BMC is actually your only single point of failure in the network. Fortunately, there's not much that goes through there. If you lose the BMC, you're going to lose access to the console. It's not part of your critical data path, and to be honest, no motherboards have more than one BMC connection anyway, so the BMC is a known point of failure, but it's not going to affect your applications if it goes down. We then have 2 of each kind of switch that we have that actually processes data. We have 2 what we call tenant switches and 2 data center switches. The tenant switches are where all of your VM traffic go. They go to 10 gigabit adapters, 2 of them. These go into a team in the Hyper-V hosts and then into the vSwitch. Because they're going into a team and we're using LACP, we have to use a technology called MC-lag, stands for multi-chassis lag, that connects these 2 switches together so they basically act like one switch. This is because in order for LACP to work, the 2 sides have to be in sync going into then the team, which then brings you all of your L2 networks together. We don't span any networks, as I mentioned before, up above the top of rack switches. We do have to have some VLANs going to the host, but that's it. Only from the host to the top of rack switch, your VLANs stop there. We then have a separate pair of switches called our data center switch, or data center network. This goes to the 2 adapters that are able to handle RDMA. So this gives us very fast SMB, very efficient SMB access from the Hyper-V host to the storage nodes. These are using Chelsio adapters in all of the compute and in the storage nodes themselves. These are not connected to a vSwitch because, as some of you probably know, RDMA doesn't go through the vSwitch. You lose the RDMA capability. So we have to have a separate physical network carved out just for those RDMA adapters, or for that RDMA traffic. All management traffic to the host go through these 2 data center switches, including cluster heartbeat for the Hyper-V host cluster, live migration also goes over here because it's also accelerated with RDMA. Now, one other thing about a single rack, if you do have a single rack, you still actually get 2 aggregate switches because we don't want that aggregate switch to be your single point of failure. The only thing about that is the rack's completely full as it is with 1 aggregate switch, so your second one would have to sit outside the rack. But there is a second aggregate switch there as well. When you get to 2 rack systems, then those 2 aggregate switches are in the top of each rack. If we now look at how these connect into the nodes, we'll start with the compute and the management nodes. We don't actually, we'll connect the compute management nodes. So each switch basically connects to 1 network adapter in each host. I mentioned before, Mellanox adapters are teamed. They go into the virtual switch. The Mellanox adapters do have NVGRE task offload capabilities. That was one of the reasons why we picked Mellanox, is for that capability. We go into the virtual switch, and that's where all your VMs are connected. There is actually no Hyper-V host parent partition access to the network through those adapters. So we don't actually put a VNIC in the parent partition on that virtual switch. So it's only for VMs. There are management VMs on there, but and tenant VMs, but no host traffic goes there. And so you can set all your VM policies, your network virtualization QoS. You can go to hosts and set ACLs if you need to in the vSwitch. And as I mentioned, all the other functions that go into the parent partition go through the data center physical network. Storage node. Well, since there are no VMs on there, we don't have Mellanox adapters. We just have the onboard Intel, and they aren't actually used. So the tenant network isn't used in the storage nodes. What we do have, though, for all the traffic are the Chelsio adapters that are, again, have RDMA enabled that's used for all the storage traffic. There's no vSwitch, no Hyper-V on these nodes, so it's from the networking perspective, they're very straightforward. So now let's actually really dive into the wiring to show you how these are all connected. I don't know if I'll spend a huge amount of time on this, but basically, every NIC connects up to every switch. I showed you that, and I showed you this. So this is your 1 rack configuration. Oh, one more. There. This is how your 1 rack configuration is cabled. You have that aggregate switch that sits somewhere outside of your CPS rack. And it's, so you still have the ability to fail over between either one of them. When you add a second rack in, you actually move that then, if you scale out. If you buy 2 racks, then they already come with the aggregate switches. You have to move that aggregate switch into the second rack, and then it has the same basic connectivity from the host up to its top of rack and aggregate, but then those data center switches also connect across to the other side. And as you add each new rack, then you get a new aggregate switch, and those connections go even from racks 1 and 2 all the way to each rack 3 and 4 as well. So again, you get your linear increase in bandwidth. Let's actually show you, and so what you get out of all that wiring cabling is redundancy. You have multiple paths up to every switch, to your top of rack switches. Whether it's on the data center or tenant networks, up to your aggregate layer, you have redundancy. And so this little demonstration here actually shows these are 2 VMs, 2 different console VMs on 2 different hosts, but they're all connected to the same top of rack switch. And so what we're going to do is show that they're both going to ping the same host. So they're going to both go to the same top of rack switch. Actually, even in this case, they'll go to 2 different top of rack switches and 2 different aggregate switches and back down to get to the same point. So you can see ECMP and work. So here you can see we check from the guest level, they're both pointing at the .1 address as their default gateway, the same .1 of their subnet. Because of MC lag, there's a floating .1 address that moves between the 2 physical switches. Now, if you look, the first hop, though, is not that .1. It's actually the .3 and .2. These are the permanent addresses that each physical switch has. Now, with the MC lag configuration, it's the .1 the permanent address that actually responds to the ping. The virtual address does not. And then you can see the second hop, which is the aggregate layer. It went to 2 different top of racks, 2 different aggregates, then back down to 2 different data center switches, but then arriving at the same host. So each one took a completely different path up and back down again. So ECMP is at work. All right, let's shift gears a bit. Let's talk about kind of going a layer up above the physical and talk about the logical network. So one of the things that we do, I talked about the address spaces that we ask for and how we carve them up. Well, those address spaces essentially get carved up into what we call logical networks. This is the layer that that VMM deals with. VMM has to be able to allocate addresses to the physical machines and to be able to allocate addresses for network virtualization. So we create these logical networks in VMM. Not all of them need to be in VMM, but most of them do. And they have different purposes. So we have one that we call infrastructure that's used for all of your host IP addresses, your data center network, those Chelsea adapters get addresses out of here. Your management VMs get addresses out of infrastructure. Your cluster, your floating cluster addresses come out of here. Live migration, Live migration does have its own address, but it goes over this network. Network virtualization comes out of the stamp private. The color coding here means dark blue comes out of the what we call the corp private. Light blue comes out of the stamp private. So network virtualization, those NVGRE encapsulated packets never leave the stamp, so it uses the private address space. BMC traffic, it stays in the stamp, it uses the private address space. We have a network that we call services. This is a network that we predefine for you so that if you're using something like the Azure websites, so the high-density web servers, these are VMs that are owned by you as the service provider, whether you're an enterprise or hoster, that do run tenant code in them. And so you want to keep them somewhat separated from the rest of your physical network. So we put them in this network that we call services that's only accessible through the load balancer, and it stays isolated from the rest of the infrastructure. We have a separate network called load balancer that's actually exactly the same, except now this is for tenant-owned VMs that are behind the load balancer. So we keep those also separate, even farther away from the rest of the infrastructure. I talked about external. We have what we call forwarding gateway front ends. These are the point-to-point transit networks between the network virtualization router and the physical infrastructure, because when you have network virtualization configured in what we call forwarding mode, that network virtualization gateway is basically acting as another router in that case, and so it needs to be able to route to a next hop, and the top rack switches need to be able to route back down again. So we have transit networks that we carve out specifically for that purpose as well. This is another view of these networks. If we actually show them kind of laid out and show you what's connected to each one. These are the same networks I showed you above, color-coded, I think close to the same way, and all their connections. So you can see the virtual switch on the top left is trunked. Basically, all of these networks come in as VLANs between the virtual switch and the top-of-rack switches. They come trunked in as color-coded. Each one represents a single VLAN. The data center networks, they come into the RDMA adapters separately, but all of these feed up into what we call the routing infrastructure. The routing infrastructure on the right side is that vertical bar on the right. Routing isn't really very, VLANs don't offer you any isolation, really, once you get up into the routers. All the traffic goes into the router, and the router will then route your traffic into any other network that it has a route to, regardless if it originated on one VLAN or another. So we do put ACLs in place to restrict traffic up there. But other than that, all these networks are basically equal once they get up into the routers. You can route from DC1 to DC2. You can route from DC1 to the VM infra. You can even route from the network virtualization address space, although that will never happen because those packets are all encapsulated and only go directly point to point. We also put ACLs on the forwarding gateways and the external network. This is because, again, these are containing tenant VMs. We don't want those to be able to get to the management infrastructure, so we put access control on those at the physical switch layer as well. And then the services and load balancer networks, the ones I mentioned before, those actually don't get routed directly by the physical switches. They actually go up and have the big IP, as I'll mention in a minute, as the hardware load balancer. That is their router. That's their default gateway. The big IP then routes outbound or does a NAT translation if it needs to, or translation to the VIP for the traffic that goes out, and inbound comes in through the VIP. So those are isolated from the rest of the infrastructure through the hardware load balancer. All right, let's look at network virtualization a little more. Let's dive into that edge cluster. Because on this diagram, actually, go back a little bit, you can see right in the middle there's that tenant network, that gray bar with NVGRE encapsulation. So network virtualization gives you the ability to create these virtual networks where VMs on it can talk to each other very happily. But at some point, they need to get out to the outside world. They need to transition from virtual to physical. And so they do that through what we call network virtualization gateway. There are two types. There's what we call forwarding. These are just basically routers that route from the virtual to the physical. In this case, the forwarding gateways route from the tenant network each one will route, one forwarding gateway will route one virtual network onto that forwarding gateway front end. And then the other mode that we have is called multi-tenant. This is where the tenant network has its own address space that's isolated from everything else. And the only way out is to either do NAT or to do a site-to-site tunnel to another data center somewhere else or another site somewhere else. We call this multi-tenant because we can have up to 100 tenants in a single gateway VM. So those are the two boxes, right? Actually, one more time. Right in the top center to the right, forwarding GWVM and MT is multi-tenant GWVM. All right, so now if we look at how we actually deploy those, in that edge cluster, every edge cluster has actually 9 pairs of VMs deployed in it, or 9 gateway clusters as we call them. 5 of them are dedicated to multi-tenant purposes. So this is so that you can have your 500 tenants per rack, each having their own virtual network. Actually, I think it's 250 tenants per rack with 2 virtual networks each. But you can get up to 500 virtual networks here, divided among your tenants. They can all configure for NAT, site-to-site. We're working on adding GRE tunneling capability as well, so you can actually tunnel through GRE without the encryption to another. If you have physical machines on a VLAN in your data center that you need to connect from CPS from your cloud to those, you can tunnel with GRE and maintain the isolation without dedicating a forwarding gateway to it. So we're working on bringing that in a future update to CPS. We also have these forwarding gateways. We pre-deploy 4 of them per edge cluster so that you can have these larger shared networks that just do routing purposes. The reason why we have these here, why you would use these instead of GRE tunneling, is that they're much more efficient. You can get, as I'll show you later, about 10 gigabits per second, in and out of each forwarding gateway. Well, actually, in and out of your gateway cluster total. The way the routing basically works, so if you're in multi-tenant mode, as I mentioned before, each network gets its own address space. Green network, red network here are 2 different tenants. Well, red network is actually purple. Did a copy and paste on that. And then when you configure it for NAT, each one gets its own front-end IP. The red network has the purple 65, 55, 10, 12. Green network gets its own front end. These are then routable on the external network. If you make that external network available to the internet, then somebody from the outside world can come in and reach these networks directly. Now, inbound would be blocked unless these tenants actually opened up a NAT rule to enable inbound mapping of ports. There's also a permanent address assigned to the gateway for site-to-site that's shared by all the tenants. That's for the site-to-site tunneling because it has to have an endpoint IP address that's also routable to the internet. Forwarding works a little bit different. So in forwarding, as I mentioned before, there's one virtual network behind the HMV gateway. These are actually really more ideal for an enterprise that's deploying CPS or network virtualization in general, because you tend to have larger networks that all share this environment. And basically, the gateway acts as a router, as I said before, and it has a point-to-point route. There's one hop that's defined in the router in the gateway itself, and then the physical switch, which is that round circle in the bottom right, it has a route that points into that virtual network address space. So that's how when a packet works its way down through the core network and eventually gets to that top rack switch, it knows, hey, 192.168.1.0, it's behind this HNV gateway here at dot 4, and so it'll go up. The reason why there are 3 addresses there is because just like the physical switches, there's a permanent address for each gateway, that's the 5 and 6, and then a floating address, the 4, which moves across as if a node goes down. And same thing in the physical switch. The dot 1 is always the floating, and then the higher numbers are the 2 permanent on each switch. So this configuration, if you're even not a CPS customer, you'll have something very similar to this if you deploy network virtualization with forwarding mode. I actually did a session yesterday where I actually talk about this in much more detail as well. So if you're not quite getting it yet, go back and watch the recording of that one. Maybe it'll help. I talked about the ACLs. We restrict the extra in a lot of the different networks so that your tenants can't get to the infrastructure. There is finer grain control available with Hyper-V extended port ACLs. We can apply ACLs on vSwitches. You have to do it directly through Hyper-V. You can do it through a script, through automation. But once you apply it to a VNIC, it'll stick with that VNIC even if the VM moves around somewhere. This is useful if you want to actually have a large shared network with multiple subnets behind it, but each one is then restricted from talking to each other. All right, finally on hardware, load balancing. We do include a fully configured load balancer. So you don't configure the load balancer yourselves. This is configured for you using the information you supply in the survey. They're pre-configured, ready to go, and they're already integrated into system centers. A lot of the services that we actually deploy in the Stamp, Azure Pack, SMA, those actually use virtual IPs that are allocated from on the big IP. And then, of course, tenants can use them too. And as they deploy service templates and VM roles through the Azure Pack, and they say they need a virtual IP, that gets allocated from the big IP as well. So we do have 2 of them, so that, again, just like everything else, one of them can fail, and the other one will still be available. Now, I showed you a little bit about the connectivity earlier. Essentially, the load balancer is the router for the networks that are behind it. So this is the load balancer network and the services network. It has a connection to each of those as the default gateway. It also has one permanent address on each and a floating for high availability. There's also a connection to the infrastructure network for management purposes. That's also a floating address as well, so that it can still be managed if one goes down. Or if the BMC switch goes down as well, it's still available. So we don't do management through the BMC and the switch management network that's in the BMC. We actually do it through the trunked networks that are going into the big IP. So that way, if that BMC, that single point of failure, goes down, we can still deploy services. All right, so let's do a quick walkthrough of what you get out of the box behind the scenes. These are all the things that when you first get CPS, this is all deployed. So you can see here we have our 32 nodes total. 2 of them are assigned to the edge cluster, 24 are the compute, and 6 for management. A bunch of services are pre-deployed, so these are all deployed in advance as well. The logical networks that I talked about, they're all pre-configured, pre-populated in VMM, so you don't have to create these yourself. You also don't need to define the network site. If you have multiple racks, the additional sites, one for each rack, so there's going to be a different subnet for each, would be placed in here as well, automatically for you in advance. So this is how VMM knows how to allocate addresses for the machines on these subnets. So here are all the ones, the forwarding networks as well. These are /29s because they're very small. We need 3 addresses for the top of rack switches, 3 addresses for the network virtualization gateways. The load balancer is already added to VMM. So here's the F5 big IP. We've pre-installed the plugins needed for VMM and added the load balancer here as well. And there are a number of VIP templates that, again, our own inbox services use because they were deployed in advance, but through service templates that have virtual IPs defined for them. And finally, we pre-create what we call the logical switch for you. From the Fabric perspective, we define the uplinks that define the connectivity of each host. So those are pre-configured as well. So we have a separate set for each compute edge and management node. And then we define a number of virtual port profiles. These are the ones that define the quality of service for your VMs and your management purposes. Now, the management VM with NLB is one of the ones that VMM pre-creates out of the box. We just reuse that for management purposes. We don't use NLB Microsoft Network Load Balancing in CPS. And then the network services. These are all those network virtualization gateways I showed you in the slide. They are all pre-deployed as well and already added to VMM and ready to use, again, out of the box. So you don't need to configure them yourself. If you do want to know how to configure them and deploy them, again, the session I did yesterday, go back and watch that one. So here you can see we've added it. This one is one of the forwarding gateways. We set direct routing mode true. That tells us if we're forwarding. And we've mapped the front ends and back ends. So VMM knows how to use it. And then we'll show you some of the services we've deployed. So these are the service templates. So all of the gateway VMs are deployed through service templates. This same service template is available to you through WebPI and the service template gallery. So the same place you go to get other service templates and VM role templates. There is a service template for deploying network virtualization gateways. So you can get that one yourself as well. So there's the edge cluster. And then, of course, these are the things that you can create out of the box. Those forward 1, 2, 3, 4, those are pre-created for you. Those are the ones that map to the forwarding network. And here it's just showing you that, yep, this is actually the same network I showed you earlier through the Azure Pack. connected through site-to-site tunnel. So this actually shows you the VMM view of that same network and how it's configured here. All right, let's move on. Let's talk about performance. How do you get a large amount of data through what can sometimes feel like a small pipe? We did a lot of work along the way of CPS to get to what we consider the maximum performance available with network virtualization. We started off without NVGRE task offload because our philosophy was, well, you don't need anything in your physical network to use network virtualization. But early on, we realized that, well, sure, it works, and you can actually get a fair amount of traffic through there, but it's not as good as what we wanted. We didn't want to have any compromise with network virtualization. So we switched over to the NICs that have NVGRE task offload. You can see that actually tripled our east-west throughput, almost tripled our north-south throughput as well. North-south goes through the virtualization gateway. Site-to-site tunneling, that's the light blue bar, doesn't benefit as much because it's essentially CPU bound at all times because of the encryption of the site-to-site tunnel. But it still did get a little bump. And then over time, we actually also increased the power of the CPU that's in the servers. That actually plays a role too, because even with NVIDIA task offload, CPU is still involved. It's just getting spread over all the available CPUs more efficiently. And so here you can see by increasing the processor performance, that's how we can achieve the maximum throughput. And you can see here, we are hitting 18 gigabits per second through those two 10 gigabit NICs. So we're about as close to line rate as you can get. The settings that we use to get there, we enabled VRSS in the guest. RSS is enabled on the host as well. It takes a little while for it to kick in. So if you are setting this up yourself, you may not see it right away, but then when it kicks in, it becomes very noticeable. And we also enable VMQ and the port profile in VMM. That's important as well. I believe we enable it by default, but we had to make sure it's there. One other thing that we noticed, and this is just an interesting fact, is that within the architecture of your server, you have what are called NUMA nodes. These are basically where your memory is affinitized and your devices are affinitized to a particular CPU. When you deploy a VM in Hyper-V, those VMs get affinitized to a NUMA node. Well, it turns out if your VM is not on the NUMA node that matches the node where your physical NIC is connected, you'll actually get a 25% reduction in the maximum throughput of your VMs. Now, as an aggregate, it's not noticeable. So as you fill up your Hyper-V host, you generally don't notice that. It's only if you actually have a VM that must have 18 gigabits per second that you would actually notice this. And it's a matter of, there are some tricks that you can force it onto a particular NUMA node, but generally the easiest way is to just deploy it until you get the right node that you need. Generally, VMs don't actually need that much traffic. So let's actually see this in action. This demonstration here will actually show you the performance from some of our testing we did. We're going to start off with basically the system at rest. You can see there's not much CPU used. There's no network traffic other than a few occasional background packets floating around. These are in the VMs themselves, running on two different Hyper-V hosts. So both you can see are idle. CPUs on the Hyper-V host. This chart, these bars show the current utilization of the CPUs of the hosts. They are also, for the most part, idle, little background fluctuation. And so what we're going to do is we're going to start up a tool. Actually, first I'm going to show you the addresses. So you can see these are on virtual networks, the 192.168 and 192.168.1 subnets. We have two virtual adapters in each one connected to a different subnet in the virtual network. And so what we're going to do is we're going to start up a tool called CTS traffic. It stands for client to server traffic. And what this tool does is it basically lets you send packets, TCP or UDP, from a listener, which is started on this machine here. So here's the listener on the 192.168.1 subnet. It's basically going to say keep transferring forever. So we started that one up, and we're going to start up another listener on the other machine, or actually a sender. So this is now sending to that other target. We're going to say 100 connections because multiple connections gives you more efficiency. And we can see things are kicking off. We're starting off at around 4 gigabits per second. You have to be a little patient here. Very suspenseful as it works its way up and that RSS kicks in. But while that's happening, the tool CTS traffic, it's available, I believe, on CodePlex. available to everyone. You can see here CPU utilization is getting spread across the board pretty well. Not fully utilized yet, but the traffic, as you can see, it is continuing to grow. We're up to 11 gigabits per second, 12. It's continuing to increase. This is going through one single VNIC on one host to a single virtual adapter on another host. We're still not up to the 18 gigabits per second yet, though, that we can achieve as a maximum. So in order to do that, we actually have to use that second virtual adapter. And so that's what we're going to do now. We're going to start up another listener on the second virtual adapter. Now, again, typically you wouldn't have just one VM on each host sending all of its traffic. So you have to think of the aggregate of all your VMs. But here goes. Here goes the second one. And now the traffic's getting split between the two. RSS has to recalculate. We're starting off at about 7 if you add them together. And it's going to start to climb as the system adjusts. We're up to 8, and going, and going, and going, and going. So it's going to slowly grow, and we'll show you the CPU now. If you look at the CPU of the host, it's actually very well utilized. Only a few processors are idle. Very efficient spreading across all the CPUs in the host now. And you can see we're going to get up there. We're going to hit that 17, 18 gigabits per second if you do the math on those two adapters. So you can see we're basically maximizing across two teamed adapters, two 10 gigabit adapters. We're using them to their maximum potential. All right, let's talk about reliability. We don't need to panic if something bad happens. I did a great Photoshop job of the guy's mouth. It was smiling earlier. He's running away from that fire. So as I mentioned earlier, CPS is designed to handle failure. Basically, any one of those purple boxes can go away. You can actually lose every single one of those. As long as the same type of device doesn't fail, your environment's going to continue to run. Now, of course, you won't get your 18 gigabits per second of throughput because you've now cut your bandwidth in half. But you'll still get 10. You'll still have your full data path. Nobody will know, none of your tenants will know that you've lost one of your switches. So it's actually pretty impressive with the amount of failure that can happen in your environment. Now, if you lose another one of these, if you lose two of the same type, you lose both your tenants, then you've got a problem and you're going to have to fix that right away. That's where you'll call our support department, and we'll work with you to get the hardware out there as quickly as possible. But we built a lot of redundancy in here. And then we did a lot of testing. So the redundancy isn't about just having hardware available. It's about having the software be able to handle these failures as well, because there are software components. If you go back here, that edge cluster has network virtualization gateways running in there that need to be able to fail over. And so we did testing. I think if you've gone to any of the other sessions, this slide was stolen from me, so I did it first. Unfortunately, my sessions later. This talks about some of the testing we did. We basically simulated 1 year, what we call 1 year and 7 days, where we built this, what's like a chaos monkey that basically just forces failures and gateways to go down randomly over time to simulate the amount of failovers you might have to do over the course of a year, as you might need to do, because of maintenance. If you have to install a patch to one of these gateways, well, that will cause it to fail over. And so we want to make sure that things can stay up and run. And we did a number of other things as well. We did live migrations, new deployments, a lot of different things to keep things up and running. And our goal was to be able to fail over for NAT and forwarding in under 10 seconds with 0 failures. So that was our goal. We fixed quite a few bugs actually along the way to get there. These bugs are now all available to all of you as well. And so our network virtualization technology is very reliable, very stable, very mature at this point. So that gives you a lot of the kind of the metrics that went into this. This is actually going to show you when those failovers happen. You'll see how quickly it occurs. Here, this is the same CTS traffic tool. It's going from a VM on a virtual network. This is just going to use the sender. Actually, this is a listener. So there's a sender already outside that's outside the virtual network and on the external network, sending traffic in through the virtualization gateway. This gateway is configured in forwarding mode. You'll see we'll get about, I think we get up to around 8, 9 gigabits per second. Takes a little while for RSS to kick in. We'll show you what the gateway clusters look like in the meantime. See, we have 2 physical nodes. This is the host cluster we're showing you first. The host cluster is both up. You can see on the host cluster, the only resource on there is what we call the provider address. We don't actually fail over the VMs in the gateway cluster. We fail over just the IP addresses. We do this because it's much faster than starting up a VM and getting then everything reconnected. If we look at the VM clusters, these are the actual gateways that are doing the routing or NATing or site-to-site. These also have a cluster. Again, it's a guest cluster. This is a cluster inside the VMs. It just fails over the configuration. So on a failover, we don't have to start up. Even though we call it active-passive, well, those VMs are actually already running. It's just the service itself within them that we fail over. You can see we're starting to pick up and get to our 10 gigabits per second, or close to it. And what we're going to do is in a few seconds, we're going to go back over, and we're actually going to fail over that, that gateway VM cluster. So if you look, we'll see that currently that gateway is running on the 34-1 node of the physical machine, and the VM is running, well, it doesn't matter which one the VM's on. We're just going to move it over. And you'll see a little blip. Start counting number of seconds. 1, 2, 3, 4, 5. There it is. You can see already traffic started flowing again. So in about 5 seconds, we failed over from one node to another. CTS traffic continued to send traffic then along the way. And slowly, performance will, as RSS kicks in again, you can see it moved from 34.1 to 36.1, so the host failed over that provider address at the same time. So these are the kind of things we do to make sure that this environment is resilient to failure. Your tenants probably wouldn't have even noticed that got failed over. Now, of course, if they're using site-to-site tunnels, those do take longer to fail over. They do fail over, but because there's some negotiation that has to be reestablished along the way, there can be up to a few minutes of downtime in the case of a site-to-site tunnel on a failover. That's that video. Okay, so in summary, so we really built CPS, as you can see, around SDN and virtual networking, taking advantage of the ability to create a physical fabric that is fixed but can be flexible by manipulating the software that runs on top of it. It gives us ability to create networks very quickly, very high performance, very reliable. So there's a lot that went into this to make it a system you can deploy in production and get up and running very quickly as soon as you get it on site. So with that, I'm here for questions. I've got about 10 minutes available. Feel free to stick around and fill out the survey or just write down this URL, take the survey, give us feedback on these types of solutions. We'd love to get your input and ask questions. And also, if you haven't gone to the booth yet, you can see all this. There's actually live system. We actually have 2 of them connected with site-to-site tunnels, network virtualization, and we can create virtual networks there for you on the fly. Go to the booth in the show, and you can see this all live and in action. So thanks. So if you have a question, feel free to go to the mic or come up here if you don't want it broadcast and recorded. Yes, go ahead.
What VM density do you get typically before these
What VM density you get before what happens?
like per cabinet? How many VMs per cabinet?
Yeah, so the scale, I believe, is 1,000 VMs per rack, if I'm not mistaken. Might actually be 500. I don't remember the VM scale, but it's in that range. It's basically based on the number of racks that you have. 1,000 to 4,000, thank you. I was right. My first thought was right.
And about how much do these things cost?
Don't ask me about pricing.
Is it like
It's price comparable to other solutions out there, and in a lot of cases actually better than comparable solutions.
$100 or $10 million or something?
It's in between those. Go talk to the booth. There are people in there that can answer those kinds of questions.
So it's basically you're buying all the hardware, all the Microsoft services.
Yep. Hardware, software, services are all in that price.
Services, so this is competing with like the vBlock
Yep.
and NetApp.
Yep.
and
Yep.
HP.
Yep. Yeah, and the per CPU cost, like if you actually look at the VM, the per VM cost is comparable and in some cases better than those.
Okay. And in this case, there's no SAN.
It's all using storage spaces, behind the scene. Yep. And there was a session yesterday that talks about the architecture, beyond just networking. It talks about storage and the compute and goes into more of the detail of, the overall CPS as a whole and its competition. It's kind of the overall architectural decisions and things like that.
And then are there future HP and other manufacturers getting involved, or just sticking with Dell?
Right now, it's just Dell. There will be other things in the future. As always, we're continuing to build new solutions, more solutions, but we don't have anything to announce today
Okay.
or this week.
And the Azure Stack is just software that you could build it all yourself.
So the Azure Pack is the Azure Pack, which is what we use. This is the existing Azure UIs that runs in production today. Another implementation of that we install in CPS, pre-install it for you. You can download the Azure Pack today and install it on top of System Center and run that yourself today. That's available to you to use today. In the future is the Azure Stack, which is now the consistent portal calling down into resource providers and down through our network controller. So that'll be something that'll be available with Windows Server 2016, but that's separate from CPS. All right. Power demand per cabinet. That I don't know. 16 what? 16 kilowatt, yeah. That was covered in yesterday's session as well. So if you watch the overall architecture session, it talks about these overall, general requirements around it. I'm the networking guy. Unless you're talking about a packet, it's not my area.
One off today.
Right, you're giving me your credit card to buy one, right, today too, right?
Yeah.
All right.
How many per month, how many cabinets per month would you say you're installing?
How many per month are we deploying? I can't answer that either. Yeah.
So why the decision to go with LACP versus ISIS and Trill, which is a true ECMP protocol? LACP isn't always ECMP in your testing wise, but what's your default match that you use?
So are you talking about between the Hyper-V host and the top-of-rack switch? So, I mean, we're dependent on what's supported by Hyper-V and the teaming modes that are available in Hyper-V. So, yeah, so what we have there, we have switch independent, LACP, and I think switch dependent. Switch independent is very good in that it doesn't require the switches to be aware that they're being teamed. As long as you have the same L2, it's good, and you'll get good outbound spreading.
I still don't understand the convergence time. Why, like in my environment, everything at layer 2 is amazing in convergence versus layer 3, right? So I was the guy that asked why BGP.
Oh, yeah, yesterday.
Why not OSPF? Because you can have fast convergence, especially on the number of networks that we can present to it. It's not impressive. So OSPF, I can have a sub-1-second convergence time versus BGP. BGP is the least used protocol on fast convergence of anything. So if you want something highly available, like it's not acceptable for more than 1 second to be down, especially down in these systems, right? So if I lose one of my edge gateways, now in theory I can affect 1,000 VMs for up to 5 to 10 seconds on my data center. I don't want to do that. I want it to fall over from the 200 milliseconds like a standard multi-chassis Ether channel layer 2 link. With other protocols, you can get faster convergence times. That's also kind of question, do you support MPBGP with IPv6 and multi-convergence?
No, we do not. Okay, so on the BGP, one other thing is BGP, part of the reason why we chose BGP is because it's also what we use in Azure at Azure scale. And Azure is using BGP. We have our own software BGP implementation that we're using in our gateways. You'll see it in Windows Server 2016. We're using it in the software load balancer and the gateways there as well. We're constantly actually making our own improvements to increase that or decrease the convergence time for BGP. There's a lot of work going on in Microsoft Research to actually get those times down. So we're working on that as well to improve there. But we use it in Azure, and it works well in Azure at Azure scale and for Azure tenants. So we think it works well here also. Any other questions?
I'm the weird network guy.
Oh, that's okay. Thanks. All right, I'll still be here for a few minutes as I pack up. If you have questions you want to take offline, thanks.